This experiment uses the principles of circular motion and Newton's second law to calculate g, gravitational acceleration. The setup for this experiment uses 2 phones, a tube, some string, and a stopwatch. The phone on the left of this diagram should be using the centripetal acceleration sensor in phoenix, and the phone on the right of this diagram should be using the acceleration without g sensor. This video should demonstrate how to perform the experiment. We want to make sure the phone in the middle is moving as little as possible and that the circling phone is moving parallel to the ground. Having a helper assist in performing this experiment will make this easier. You want to make sure you keep track of the period of time the circling phone is in circular motion with as little vertical movement as possible, by starting a stopwatch at the same time as the centripetal acceleration sensor. After doing that part of the experiment, you should measure the mass of each phone with a scale. Then find the average centripetal acceleration recorded by the circling phone between the start and end time of circular motion with minimal vertical movement you observed on the stopwatch. If you assume that the central phone was stationary, the system was not moving vertically, the tension at both ends of the string are equal in magnitude, as well as air resistance and friction being negligible, then gravitational acceleration can be calculated like this. The scalar magnitudes of the central phone's weight and the 2 tensions of the string should be equal. The y component of the tension on the circling phone should be equal in magnitude to the circling phone's weight. Angle theta on the diagram can be found by finding the inverse sign of the ratio between the circling phone and central phone's masses, because g cancels out of that equation. The centripetal force on the circling phone is its mass times the average centripetal acceleration found earlier, divided by the cosine of theta, will be equal to the weight of the central phone. The centripetal force multiplied by the tangent of theta will equal the circling phone's weight. The weight of each phone divided by their respective masses will equal gravitational acceleration. We performed the experiment 12 times and got 24 values of g. The average of the 24 values is 13.809658181 meters per second squared, and the uncertainty was estimated by finding the uncertainty in the mean value of g by finding the range of values divided by 2 and divided by the square root of the number of values. Our final value for g was 13.8 plus or minus 0.8 meters per second squared.
For the dropping phone experiment, we will take from our understanding of Newton's second law to drop a phone from rest. If the phone is in freefall, it will have the gravitational acceleration since gravity is pulling it downward. The material needed for this experiment is a phone and a soft surface. We will use phoenix, acceleration without g sensor, to set the timed run function to starting from 0.3 seconds to 0.6 seconds. How the experiment will be performed is we press the start button to start the sensor, and immediately drop the phone from rest such that the phone is in freefall for the entire duration of the timed run, which is 0.3 seconds to 0.6 seconds. To collect the data, press the absolute button at the top of the page and record the value for absolute acceleration, which is shown. After we perform 15 trials, we will take the average of all the absolute acceleration values by adding up all the values and dividing by the number of trials, which in this case is 15. The average calculated will be our calculated gravitational acceleration.
This is the inelastic collision method to determine the experimental value of gravity. The following physics principles and concepts have been used: conservation of energy, kinematics, and inelastic collision. The materials needed are a bouncy ball. This doesn't have to be a rubber ball. It could also be a volleyball or a basketball, a tape measure or a ruler or a meter stick, the 5 Fox axis. For this lab, we will be using the acoustic stopwatch in sequence setting, as well as tape or some sort of marking device so that you can drop the ball from the same height each time. Data collection will be taking the time intervals that 5 Fox gives us, We will also be documenting the height at which the ball is dropped from, as well as the first rebound height. This will be used for calculations later. So how exactly does it work? It's pretty simple actually. We are basically dropping the ball, and the sound that the ball creates when hitting the ground is what starts and stops the acoustic timer. These values are put onto a chart, and from there we can calculate the experimental value of gravity. So this is the Excel sheet that all the data has been inputted onto. There is the experiment number, there's the distance of free fall, there's the first rebound height, which is an estimate, as well as the display times that Firefox displays. From that, we can calculate the ratio of heights by doing distance of free fall divided by first rebound height, and from there we can also calculate the second rebound height by doing first rebound height divided by ratio of heights. Using all of that, we can determine the acceleration due to gravity. This is the equation A equals 2d over t over 2 squared. T over 2 just represents the time it takes for the ball to drop from the first rebound height back to the ground. Continuing on, uncertainty. So what we've done here is taken the maximum and the minimum and then divided it by 5. As shown here, we did it both for height as well as time. We've multiplied time by 2 since we're squaring it in the equation. After adding these percentages up, we convert it back into meters per second squared. Doing that gives us the final result of 3.5 meters per second squared plus or minus 0.7 meters per second squared as our experimental value of gravity. This is the pendulum method for determining experimental value of gravity. The main physics principles used in this method is simple harmonic motion and pendulum motion. It is known that the period for a pendulum depends on its length and the acceleration due to gravity. Thus, we can experimentally determine the acceleration due to gravity using a pendulum. The pendulum itself was created using a plastic bag holding the phone suspended by strings of twine. The plastic bag was folded to fit the phone snugly to prevent it from sliding back and forth during the oscillation. The twine was connected on both sides of the plastic bag to stop the ball from rotating, and was also marked at pre-measured distances of 5 centimeters apart. The pendulum was suspended by a wooden rod between 2 chairs. The period was measured using the Firefox app as the phone was the bob of the pendulum. The length was determined from the pre-measured markings on the twine. After Firefox gave a steady reading for the period, the length was switched to repeat the experiment over a span of 50 centimeters. The data and the period of the correlating length were all recorded and processed in Excel. This is the Excel sheet with all the data. The acceleration due to gravity can be calculated using the formula T equals 4 pi square root G over L, which can be rearranged to G equals 4 pi squared T over period squared. The uncertainty was estimated by taking the range of the calculated G values and dividing it by 2 times the square root of the number of trials performed. It is found that the acceleration due to gravity is about 9.8 meters per second squared with the uncertainty of 0.004 meters per second squared.
Hello. For our experiment in determining the acceleration due to gravity, we used a rolling cart on a ramp and a phone with the magnetic ruler function on Firefox. Now, the magnetic ruler can measure the magnetic field the phone is in. As the cart is rolling down the ramp, the phone will measure the magnetic field due to the magnets placed at exactly 1 meter apart. From the magnetic ruler function in Firefox, we can analyze the graph and determine the maximums and the minimums in the magnetic field. From that, we can determine the time between the 2 maximum magnetic fields.
Since we know that the distance between the two magnets is exactly 1 meter, using the ruler of course, we can then use kinematics equations to determine the acceleration down the ramp. Then, using the inclination function in phi fox, we can determine the angle of the ramp. With this angle, we can use a free body diagram and dynamics to determine the acceleration due to gravity.
In this spring scale and ramp method to calculate the acceleration due to gravity, the gravitational force equation, Fg equals mg, as well as trigonometric functions, are used to determine gravitational acceleration as the primary physics principles. This method will use the Newton spring scale and different incline slopes measured with the inclination feature on phi fox to determine the gravitational force for a specified mass and ultimately the acceleration due to gravity. The mass of the cart, m, and the gravitational force of the cart parallel to the inclined ramp, Fgx, will be measured. This lab will also require a Newton spring scale, a centigram balance, or any instrument to measure mass, a cart, and various inclined ramps.
For the procedure, measure the mass of the cart using a centigram balance and record this mass. Next, place the inclined plane onto a flat surface and record the angle of inclination using the inclination feature on phi fox by placing the phone flat onto the ramp. Adjust the Newton spring scale if needed by zeroing it correctly. Hang the cart off a Newton spring scale on the inclined plane and record the shown force measurement. Make sure that the Newton spring scale is directly parallel to the inclined plane to ensure a correct measurement. Repeat this process for all the different inclined planes. The data was recorded in a table format that outlined the steps of calculation to achieve the final value.
Draw a free body diagram of the forces acting on the cart to help visualize the calculations. Split Fg into Fgx and Fgy components parallel and perpendicular to the ramp. Since theta and Fgx is known, Fg, the gravitational force acting on the object, can be determined using Fgx over sine theta. Next, inputting the mass of the cart and the determined gravitational force into the gravitational force equation, Fg equals mg, the acceleration due to gravity can be found. This calculation process should be repeated for all the different inclines to find the average value of g and the amount of uncertainty. The final value of g, the acceleration due to gravity, was found by averaging all the trial values. The uncertainty for this average was calculated by dividing the range of the values by 2 times the root of the number of experiments overall. A cart was used to minimize friction, but possible outside force and uncertainty in the mass, measured force, and inclination angle would have still been some sources of error.